Okay, I suggest that we start. So maybe Dmitry, you can introduce the speaker and.
Yes, hi everyone, thanks for coming. So today we are going to hear a tutorial about the VyPR framework developed by Joshua Dawes and colleagues from CERN and the University of Manchester. And in particular, we will see how to use that framework to analyze the performance of Python-based web services. And Dejan will play the videos. There are 5 of them, and we will make short breaks, and there will be room for questions in between the videos.
So in the next 1 hour and 30 minutes, you can expect first an introduction to VyPR, which is a framework for performance analysis of Python programs, and then an in-depth description of the past 3 years of contributions to both the runtime verification and software engineering communities made by VyPR and its underlying theory. Finally, we will give a live demonstration of VyPR being used to analyze the performance of a real-world system used at the CMS experiment at CERN. All of the materials for this tutorial can be found at various links. For example, the VyPR project website can be found on the GitHub IO page. The tutorial materials can be found in a directory on the project website. And finally, the source code of all of the components is released on GitHub under the GPL v3 license. So we'll begin by thinking about the problem of gaining insight into the performance of a program. This typically involves the use of a profiler. So in this case, we focus on Python, for which we could use the C profiler tool. In this example you see taken from the documentation, we import the C profile library, we instantiate something from it, and then we use these enable and disable methods. And these enable tracing, which is a facility provided by the Python interpreter. And this would generate fairly detailed output of function calls, their frequency, and the time they took, which would be very useful. While profilers are very easy to use, and the Python interpreter makes it very easy to implement one with all the facilities that it provides, the large amounts of data generated when analyzing performance data with respect to varying inputs can be difficult to analyze. There are tools to help us do this, but it's still tricky. Further, profilers measure single types of quantities, for example, just function calls, and these are also measured as independent quantities with no relationship to each other. Further, checking of constraints is possible offline, but checking constraints over combinations of quantities with no real relationship to each other becomes quite difficult. Now, what about explaining performance deviations? Explanation with information collected by profilers is restricted by the quantities that they measure, and most profilers focus on function calls, so explanation normally looks like, when the call tree looks like this, then we have a problem. Further, low-level behavior of programs, for example the code inside functions, is out of reach, at least in the Python setting, because tracing is required, and in this case, the amount of overhead that is generated would completely distort the performance being measured. So in general, the ability to explain performance deviations using profilers is quite limited. Our effort to remedy this situation takes the form of the VyPR framework, which enables software engineers to write source code level specifications about how their Python program should behave. With minimal modification of the source code by a software engineer, VyPR performs instrumentation before runtime, monitors for agreement with the specification during runtime, and then stores verdict data ready for it to be analyzed by software engineers offline using our sophisticated analysis tools. The VyPR framework offers several advantages. For example, conservative instrumentation based on specifications means overhead is usually quite low. A combination of the code required to be added to the codebase to activate VyPR and the conservative instrumentation means that the intrusion into the monitored system is minimal. And finally, formal specifications written in a low-level and rich language allow, firstly, automatic checking of constraints over multiple quantities measured at runtime, and secondly, multiple types of explanation to be offered whenever a given specification is violated. Now, in order to describe the VyPR framework, we will present the past 3 years of work that has made contributions to both runtime verification and software engineering. These contributions include a specification language, which includes the syntax and semantics as usual, a conservative instrumentation approach, and with this we will give worked examples and visualization, an efficient monitoring algorithm with which we'll also give a visualization, machinery for explanation of whenever a specification is not satisfied by a program run, and finally sophisticated offline analysis tools that take the form of a web-based application and a Python-based analysis library. To conclude, we will show how all of the material presented has helped us to analyze the performance of a real system running at the CMS experiment at CERN. So let's take a look at our specification language contribution, which is specifically aimed for software engineers to use in the software engineering process. In particular, we designed a low-level temporal logic with the aim of providing a tool that can be used by the average software developer writing Python code. The result of this process was control flow temporal logic, or CFTL, and this was introduced in the SAC SVT conference. The distinguishing characteristics of this specification language include the fact that no instrumentation mapping is required, meaning that if we take an arbitrary formula written in CFTL, the meaning of that formula with respect to the program that it's been written over is immediate. Further, no knowledge of the usual modal operators such as next, until, or always is required, and this makes writing these specifications a little bit more straightforward for software engineers. And finally, the combination of the previous two, that is no instrumentation mapping and no knowledge required of the usual modal operators, means that a software engineer needs only to think about the source code that's actually being monitored rather than thinking about the mathematical background of their specification formalism. And this makes the specification process more straightforward. A CFTL formula expresses a property that should be held by a single execution of a function. This means that when we come to write a specification of how a system as a whole should behave, we do so by writing a set of specifications over each function in that system. So in order to write a single CFTL formula, we need to know the general form that we should follow. Each formula consists of universal quantifiers to capture events that happen at runtime. We'll develop a precise definition of events later. And then we have a constraint to check at each of these captured events. This structure of formulas allows us to first identify where in a program's runtime we'd like to check something, and then precisely define the constraint that we'd like to check as a mixture of various constraints that are allowed by the syntax and semantics of CFTL. Our first step in developing CFTL formally involves developing a model of functions, that is a static model that we can build. So we start with a representation of the source code of a function called a symbolic control flow graph, and you see an example on the left. The SCFG of a function is a directed graph encoding potential changes of program variables or functions and reachability and control flow. For example, on the left you see that one of the vertices near the top we have a loop with the variable I being changed, and then we encode the loop structure as a cycle in the graph. We're going to see plenty more examples of symbolic control flow graphs derived from real programs over the course of this tutorial. Here we see an example of a symbolic control flow graph on the right, with its corresponding program on the left. So you see that constructs such as for loops, as we have here in the program on the left, are encoded by vertices and then cycles, as I mentioned before, but we also have this notion of a symbolic state, which encodes the potential change of a variable or the potential call of a function. For example, we have b equals 10, and this corresponds to the vertex b in the symbolic control flow graph. But notice that there's no information about concrete values stored in this because it's only a statically computable structure. Similarly for the function call that you see highlighted below. So in this case we have a change of the variable result 2, but then we also have a call of the function calculate something. So in this case we're not encoding anything about the concrete values that might be obtained, rather we're encoding information about the possibility of certain things happening like variable changes or function calls. Finally, the edges in a symbolic control flow graph also have meaning. For example, instructions in the code that are consecutive also have edges between them in a symbolic control flow graph. And this leads to the fact that edges model the potential computation that would happen to get from one state to the next. We now need a model of function executions because it's over these structures that we will actually define the notion of truth of our specifications. For control flow temporal logic, we represent an execution of a function by a dynamic run, which we denote by D here. A dynamic run can be described as a sequence of checkpoints reached by a program at runtime. To look more closely at a dynamic run, here we see highlighted in blue an example of a concrete state. Now this is a triple whose first element is a symbolic state from a symbolic control flow graph, whose second element is, we say, a concrete mapping from variables in the program to concrete values that they obtain, and the third element is a timestamp. So you see, if you look at the multiple concrete states that are in this dynamic run, the timestamps are monotonically increasing, as you would expect from something generated by the runtime of a program. Intuitively, concrete states are instantaneous checkpoints that a function execution must attain. We can then pair these concrete states to make transitions. And these transitions model the computation that occurs to move the function execution from one concrete state to another. We normally denote these transitions by using this arrow-like syntax. So on the left you see we have a normal concrete state, and on the right we have a separate concrete state. So normally the two concrete states in a transition will be consecutive. Now the fact that concrete states are related to symbolic states has the consequence that a dynamic run, being a sequence of concrete states, can be related to a path through a symbolic control flow graph. This means that our representation of a run of a program, the dynamic run, can essentially be seen as a path through a symbolic control flow graph, which is ultimately our representation of a program. With symbolic control flow graphs and dynamic runs introduced, we're in a position to talk about the semantics of control flow temporal logic. The FTL semantics is built on dynamic runs, not surprisingly, and here we see that if we take a CFTL formula with the normal form that we introduced before, we have the quantifiers on the left and then the innermost quantifier-free part on the right, then we can begin to say what exactly these things actually mean that are in the formula. For example, before we said that on the left the quantifiers capture certain events that happen at runtime. And now we can say precisely that these quantifiers capture sets of concrete states or pairs of concrete states, which we call transitions. Further, we can introduce the notion of a predicate and say that a predicate is a rule that defines which concrete states or transitions should be used when evaluating the CFTL formula. And finally, we can now say that the innermost quantifier-free part of the formula should be evaluated at each one of these concrete states or transitions identified by the predicate gamma and bound to the variable q. Now, to go into more detail on the subject of predicates, the FTL semantics includes multiple predicates that can be used to capture either sets of concrete states or sets of transitions. Here we see two examples. So in the first one, we use the predicate changes and then a variable x. So x here is a program variable, and we want to capture every single concrete state in which x has been changed. Now we say formally that a concrete state changes a variable, in this case x, if the symbolic state with which it's associated indicated a potential change of x. And using this definition, the predicate changes x would capture all such concrete states and bind each one individually to the variable q, so that can be used in the innermost quantify-free part of the formula. We now pass on to the next predicate, which is calls calculate something. So this is a similar idea to the previous predicate, except in this case we capture transitions. And again, we use the symbolic control flow graph information that's encoded in the concrete states. For example, in this case we have a transition, which is a pair of two concrete states. And then we say that a transition satisfies this predicate if the second concrete state in that transition points to a symbolic state which indicates a potential call of the function calculate something. Here we see an example of these two predicates being applied to an actual dynamic run. So in this dynamic run we have a number of concrete states, and then we have a transition between each one of these concrete states. You see the top left we have the predicate changes x, and we suppose that this identifies a state, and then the top right we have the predicate calls of calculate something, which identifies a transition between two concrete states. We can go further with predicates and define more complex ones by combining multiple. To help with this, CFCL introduces the future predicate. So you see here that we have first a predicate changes x, and this binds appropriate concrete states to the variable q. But then we say that, okay, given this variable q, whichever concrete state it's holding at a specific time, we want to look in the future of that concrete state and find all of the calls of the function calculate something. The result of applying these two quantifiers to a formula in CFTL is that the innermost quantify-free part of the formula will be evaluated using pairs. In this case, the pairs will consist of concrete states, captured by the first quantifier, and then transitions, captured by the second quantifier. An important detail to take note of in this case is that if there are multiple future calls of the function calculate something after a single change of x, then multiple pairs will be generated with the same change of x, but a different call of calculate something in the future. We see this idea illustrated here. For example, if we suppose that state 1 is identified by the predicate changes x and therefore given to the variable q, and then suppose that first of all the transition between state 2 and 3 satisfies the predicate calls of calculate something, but then also the transition between state 3 and 4 satisfies the predicate calls of calculate something, then we have this repetition. In particular, we have two pairs, consisting of a left and a right-hand element for Q and C. And in each of these two pairs, Q is given the same value. And this is because we have supposed that there are multiple calls of calculate something in the future of state 1. Therefore, these will be identified by the future predicate. Now, once we've defined our quantifiers and thought about which parts of the program run that we want to select and apply constraints at, we need a way to write the innermost quantifier-free part of our formula. Now, the syntax provided by CFTL for this is extensive, and we won't describe it all because it would take a few slides. Instead, I'll give some examples. So in this first example, we consider the property that for every transition that satisfies this predicate, so every transition that is a call of the function calculate something, then we want to check whether its duration was less than 1 unit of time. So you see that we use a quantifier with the variable t and the predicate calls of calculate something. So each transition that satisfies this predicate will be given to the variable t, and then for each value of the variable t that we derive via this predicate, we use the duration operator, which is defined by CFTL, to take the difference in the timestamps between the two concrete states used in the transition. Once we've measured the duration, CFTL then makes it easy for us to compare this to a numerical value. We can then easily write more complex constraints. For example, in this case, we have one quantifier, but then the innermost quantifier-free part of the formula takes advantage of the standard Boolean connectives that CFTL supports. For example, in this case, we say that for potential changes of x, if x is greater than 10, so on the left-hand side of the implication, then the next call to the function calculate something should take less than 1 unit of time. As you see on the right-hand side of the implication, we have the duration operator, but then inside the duration operator, we introduce a new feature of CFTL, which is the next operator. And this takes a concrete state or a transition, so in this case, the concrete state held by the variable q, and then searches forward in time for the next concrete state or transition that satisfies the predicate given. We can also define more complex specifications using multiple quantifiers like we saw before. For example, in this case, we first use the predicate changes and bind every concrete state that this identifies to the variable q. We then use the future predicate along with calls of calculate something to bind future transitions that satisfy the calls predicate to the variable t. But then we introduce a new operator, which is time between. And the idea here is that we can give this operator two states, and then reason about the time between these two states. So you see that we can give it directly the variable q because this already holds a concrete state. But in the case of t, this holds a transition. So first we have to use the dest operator to obtain the second concrete state in the transition. And once we've done this, we can compare the time between these two states to a numerical value.
Okay, so yeah.
Yeah, are there any questions so far? I would have one. Maybe I would like to. So you said you don't have modalities in your language, but you do have future and next. So what are those?
Yeah, so we sort of, I guess we do have temporal operators of some kind. We just don't call them the classical sort of linear temporal logic versions of next or eventually or things like that. We like to say that we define them in a slightly more intuitive way. For example, when we say the version of next in our language is referring to the next thing in the future that satisfies some predicate, which is different to the conventional definition of next.
It's more like eventually.
Yeah, exactly. So we do have the temporal behavior, which is why we allow ourselves to call it temporal logic, but it's not the conventional form, as you say.
And what is the reason for not using the more conventional? Is it this intuitiveness that you feel that the temporal logic does not have, or are there other reasons?
Yeah, it's basically the intuition involved. So one of the things that happened when we first started to think about doing this at CERN, we had a meeting and I put some examples of linear temporal logic up on a screen. And let's say it took about half an hour for people to understand what the different modal operators meant. And I thought, well, if this is the audience that is going to be using this tool eventually, and there's so much, let's say, difficulty with getting to grips with the level of abstraction in LTL or languages like that, not necessarily just LTL, then we might have a problem. So one of the requirements from the start was that there would basically be no maths involved, no abstraction, and no intense background to learn. You would just be able to pick up some documentation, and after reading one paragraph of instructions, well, more than one paragraph, but after reading some brief instructions that are basically software documentation, mathematically based, then any software engineer who writes Python code or any other code should be able to write these specifications.
Are those software engineers your customers, or are those physicists?
It's a bit of a mixture. That's
Okay.
so far. So we have there are people interested who are physicists turned into software engineers, which is an interesting transformation to happen. We have pure software engineering people, and yeah, there are inevitably physicists who write software. But yeah, we generally aim to solve the problem that we don't want people to feel like they're writing mathematics when they're specifying or when they're analyzing how their program behaves. We want them to just be able to use it as a normal tool. So.
And did you look at the expressiveness of your language compared to the temporal logics? Like, can you encode your language in to some LTL or MTL formula, or did you not look at these kind of questions?
So we've thought about this, not completely formally. We haven't spent a lot of time on it, but we know that. So it kind of depends on what you pick as the trace that you're using in LTL. So you could pick, if you pick a sufficient trace, then LTL is more expressive, and this is one of the sort of the trade-offs that we get in order to make a language more intuitive, we have to throw away the expressiveness at some point. Whereas in order to get expressiveness, it seems like the further towards really, really expressive you go, the more people you're going to lose on the way. So it's.
And another question I had regarding this symbolic control graph. So do you need it only to define the semantics, or I didn't quite get, or do you also use it when monitoring?
So you'll see how we use that in instrumentation, I think, in the next part. So.
Okay, good.
So I guess we can continue then.
Sure. Just a moment, let me share the screen.
We'll now look at how to express CFTL specifications using Python code, with the intention of allowing software engineers to easily express their behavior requirements. The specification library that we provide is the first interaction with VyPR that a software engineer has. It's a translation from the mathematical formalism that is control flow temporal logic to a structure that can be used by VyPR during instrumentation and at runtime to check whether the specification given actually holds. So with this in mind, it's vital that first, software engineers can easily express their requirements using this library, and second, feedback to mistakes in specifications is useful. For example, if an engineer accidentally compares a numerical value to a string, then they need to be told. The library that we provide to allow engineers to convert their CFTL specifications into Python code is called PyCFTL. And you see here the first example of a translation from the CFTL formalism into Python code. So here we have a single quantifier, and then the innermost quantifier-free part of the formula just performs a simple duration comparison on the variable given by the quantifier. And this is translated into Python using the PyCFTL library. First by converting the quantifier into the for all syntax you see here, where we also use Python's keyword argument feature to implicitly define the variable t. We then express the innermost quantifier-free part using a lambda expression. So for example, here we have the variable t, and in the original CFTL version, we used a duration operator to measure its duration. The equivalent in PyCFTL involves taking the variable t, which we assume contains some representation of a function call derived at runtime, and calling the duration method on it. We can then use Python's standard comparison operators, here we have less than, and write a very easily readable piece of code that clearly encodes the fact that we want the duration of whatever function call is held in t to be less than 1 unit of time. As another example, we take the CFTL formula that we saw before with implication, and show how in PyCFTL we can use the if-then syntax to encode our implication. We then treat the variable q as a state because it's a concrete state, and first refer to the value that it gives to a variable x, and ask if this is greater than 10, and then we also refer to the next function call along by using the next call method defined on it. Now significantly we see that once we've used this next call method, the result of that will be a transition, and as you saw in the previous slide, transitions define the method duration so that we can measure how long they took. So in this case, we start with q, we ask for the next call of the function calculate something. This gives us a transition on which we can call the duration method to obtain the time that that transition took. And then we can use the standard comparison operators that Python provides. Finally, we see how to translate the time between operator into PyCFTL. And as can be seen here, there's almost no difference. In fact, in this case, the PyCFTL code gets slightly more intuitive because instead of having this dest operator that's present in the original CFTL version, now we have this variable t that holds a transition, and we can call the method result on it, which gives us the concrete state immediately after it. So to conclude this brief introduction to PyCFTL, we provide an intuitive library to software engineers so that they can express the behavior requirements of their programs in an intuitive way and in a language that they're already accustomed to. Because of the way that PyCFTL is implemented, that is, it overloads most basic operators on its objects to allow a cleaner syntax, we also have the advantage that we can provide useful error messages. For example, in this specification, we capture all of the transitions that are calls of the function calculate something, and then we measure the duration, but then we compare that to a string. So this is clearly not a correct specification. Because of the way that PyCFTL is defined, we can detect this and give the error here that you see. We're now going to address the problem of how to extract the data from a program run so that a given CFTL specification can be checked. We call the problem of determining which parts of a program from which we need to take data to check the satisfaction of the CFTL specification the instrumentation problem. And the solution to this problem begins by saying that, given a dynamic run, one of its concrete states is relevant if the corresponding symbolic state was identified by instrumentation as being needed to decide whether or not the given CFTL formula was satisfied. In general, our goal is to reduce the number of concrete states that are in a dynamic run which are not relevant with respect to a given CFTL specification. The major consequence of solving the instrumentation problem badly is that there will be more overhead at runtime because the monitoring algorithm will spend more time working out whether it really needs some of the data that's been observed. On the contrary, if the instrumentation problem is solved well, then the monitoring algorithm can have confidence that the information it's getting at runtime is mostly needed. First, we need to define the instrumentation problem formally. To do this, we first take an example CFTL formula because instrumentation takes place with respect to one of these, and then we say that the instrumentation problem involves determining the set of symbolic states such that a dynamic run containing only relevant concrete states with respect to those symbolic states contains enough information to decide whether the CFTL formula holds. This is just a slightly more formal expression of the notion that we discussed in the previous slide. So ultimately, we have to completely remove from the dynamic run in question any concrete states that correspond to symbolic states that instrumentation determined were not useful with respect to our formula. For example, in the case of the CFTL formula on this slide, we have, first of all, that we want to capture concrete states which change the variable a, and then we also know that we want to capture transitions that were calls of the function calculate something. Now, by looking at this formula, we know that these are the only two variables or functions that we care about, so anything that doesn't involve these we don't have to instrument. To describe our approach to the instrumentation problem, we first have to introduce some new terminology. So here we have an example CFTL formula, and as we've already mentioned, we have quantifiers and we have variables. But then when we look at the structure of the innermost quantifier-free part of the formula, we have two new terms that we have to introduce. The first of which is an atom, And these are the parts of the formula that would be leaves if we were to look at the syntax tree of the formula with respect to the Boolean operators involved. The next new term is the subatom, which comes into play when we consider atoms that take measurements at two different points in runtime. For example, in this case we have Q and dest of C. So Q forms one subatom and dest of C forms another. Notice that we only refer to Q as a subatom and not C. And this is because the intuition behind subatoms captures the final concrete state or transition that's given to an operator. If we then zoom into the structure of a CFTL formula further, we can define the set of base variables of an atom. So in this case we have what we call a mixed atom, and as we saw before we have subatoms Q and dest of C. But these two subatoms are based on the variables Q and C. So when we think about the set of base variables of an atom, we mean the actual variables from the quantifiers that we used to derive the concrete states or transitions used by that atom. When we perform instrumentation, the output of our approach is a tree which we call H5. This tree will help us to organize our instrumentation data in such a way that it can also be used to optimize the monitoring process. Our first step in constructing the tree H5 is to inspect the quantifiers of a given CFTL formula. So here we have an example with two quantifiers we have highlighted in purple and blue. And the first quantifier looks for concrete states that are changes of A. And as we saw before, for one of these predicates to identify a concrete state, this means that the symbolic state associated with that concrete state has to indicate that A could change. So in this case, it makes sense that the vertices in the symbolic control flow graph on the right that contain the letter A should be highlighted by instrumentation. Further, for each such vertex that indicates a possible change of A, we have to reach forward in the graph to find pairs of symbolic states whose second symbolic state indicates a call of the function calculate something. And this is how we determine the parts of the symbolic control flow graph that would correspond to the second quantifier. Now once we've performed this traversal with respect to the quantifiers, in this case we would get a set of pairs, which we call static bindings. Formally, each of these static bindings is a map from variables from the CFTL formula to symbolic states or edges in the symbolic control flow graph. Finally, we denote each of these static bindings by beta, and highlight on the symbolic control flow graph on the right here a subset of the static bindings that would be derived with respect to this specification. And now that we've defined static bindings, we can introduce the first level of the tree H5. In particular, this level of the tree consists of the static bindings derived. Now if we look at the symbolic control flow graph shown on the left, it's clear that more than 3 static bindings can be derived, but we just show 3 here for the sake of illustration and to save space. The next step in instrumentation, once we have static bindings, is to inspect the atoms and the subatoms of our CFTL specification. So as we saw before, time between less than 0.5 makes an atom, and Q and dest of C makes subatoms. Atoms define the type of measurement to take. Here the atom is time between, so we will clearly need to measure 2 timestamps. And subatoms define where to take the measurements. In order to determine where to take measurements, we have to translate each atom to have meaning in the symbolic control flow graph. We call this lifting and define the lift function to take a subatom along with a static binding. The intuition is that from a static binding we can take a symbolic state or an edge from the symbolic control flow graph, and then we can use the subatom to determine the kind of traversal that we have to do from the given point in the symbolic control flow graph. By performing this traversal, we then determine the parts of the symbolic control flow graph to which the relevant concrete states that need to be in our dynamic run must correspond. Here we illustrate the process of taking a static binding, in this case beta 1 and beta 2, and lifting the subatom dest of C according to that static binding. So the subatom that we've been given is based on the variable C, so we will care about the value to which the static binding beta 1 maps C. In this case, C is mapped to a pair of symbolic states or an edge in the symbolic control flow graph. And we know from the subatom that we have that we care about the destination of that edge, which is the vertex that indicates a change of the variable result1 and call of the function calculate something. We perform the same process below for the bindings beta 2 and beta 3. It's exactly the same idea. So ultimately, by applying this process in generality, from a given static binding, we can break apart the structure of the innermost quantifier-free part of a CFTL formula and determine all of the parts of a symbolic control flow graph that are relevant to each part of the innermost quantifier-free part. Ultimately, we can summarize this process in terms of an algorithm. So for each static binding that we derive, which we call beta, And then for each atom or subatom alpha, we compute the lift function given alpha and beta. The result of this algorithm is the tree, H-phi, whose first level is static bindings and whose second level is atoms. The leaves of this tree are then necessarily the symbolic states or edges from the symbolic control flow graph that have been deemed relevant by the instrumentation algorithm. By organizing the results of the instrumentation algorithm into a structure like this, we make the instrumentation information useful to the monitoring algorithm. We will see precisely how this works later on in the tutorial. In order to demonstrate exactly how instrumentation works, we've built a visualization tool that allows us to replay real runs of the VyPR tool. So this is our visualization tool for the VyPR framework. This screen right now is the instrumentation screen, and at the top you see we have a set of events that happen during instrumentation. So we begin with the first event that signals the beginning of a function being processed, and then we have the events for a new binding, a binding being completed, another one, and another complete binding, and then the final events for determining the actual instrumentation points with respect to those bindings. And this is the symbolic control flow graph for the code that we monitored in this case. So if I now begin to scroll through these events, you can see that when I click next, first of all, for a new binding, I get the variable that I care about in the specification, and then I get the point in code that's been identified, and I get a new binding on line 9. If I then go to the next one, I see that the binding was completed because there's only one quantifier here. And then if I go to the next event again, we see that we're on this quantifier again because, again, there's only one quantifier, but in this case we've seen another line, another statement in the code where what happens at runtime satisfies our quantifier is captured by it. So here you see line 15 appear here in the binding tree. So when I click next, I see that this binding is again completed because only one quantifier. And then I go on to finding all the set of instrumentation points. So for binding 0, which is line 9, you can see that we only have one atom. We have one atom that has multiple subatoms, so we have S, and the next call of calculate something along from S. So I have just this one atom, but then I have the left-hand side, which is S, and I have the right-hand side, which is this next call of calculate something along from S. So for the left-hand side, you can see that I have line 9, and of course I have the change to A, which is identified by the quantifier. But then for the right-hand side, which is the next call of calculate something, I have line 10 and line 11. So we care about line 10 and line 11 because this is where the transition actually happens. So if you look at the specification, we have s.next call of calculate something .result. So what we really care about is the state immediately after it, but we need to know about the transition itself, and the transition itself happens starting immediately after line 10 up until immediately after line 11. However, we only care about what happens immediately after line 11. So if we go on to the next event, we see something similar. Where we have line 15, which corresponds to the change of the variable A, but we also have line 15 to 16, which is the next transition that satisfies the right-hand side of the atom. And we do the same thing here. So the transition actually happens between the end of line 15 and the end of line 16, but because the specification is asking for the results, i.e. the state immediately after it, we only care about the state immediately after line 16 has been executed. Now, this instrumentation tree is what we showed earlier, and this is the first thing that is constructed by the instrumentation process. So you see that the first level is the bindings, the second level is the atom indices, the third level is the atom subindices, so we have the left-hand side and the right-hand side here, which corresponds to subatoms S and S.next call. And then the leaves are the parts of the symbolic control flow graph that we care about. So in this case, in the visualization tool, we care about the actual lines because it makes it easier for users to see. Once we've constructed the tree H-phi, we see that there's some overlap between bindings. In particular, in this case, we see that the vertex with the variable change result 3 and the function called calculate something, and the vertex with the variable change A is repeated across multiple bindings. When it comes to actually placing instrumentation code in the target program, this overlap will translate into repeated measurements and ultimately unnecessary overhead. So our next step in instrumentation is to eliminate this overlap, thus reducing the chances of unnecessary overhead. By inverting the instrumentation tree that we construct to map symbolic states to bindings, we can place only one instrument per critical symbolic state, thus avoiding repetition and reducing unnecessary overhead at runtime. The final stage of instrumentation is to actually place the instrumentation code in the target program. To do this, we take advantage of Python's intermediate bytecode representation of programs. In particular, normally, execution of a Python program involves reading in a source file, which is .py, converting that to bytecode and then interpreting the bytecode. This bytecode can be made persistent in PYC files, which are essentially compiled Python files, and these can be executed without the need for conversion from source to bytecode. The instrumentation process performed by VyPR generates Python bytecode rather than Python source code. We're now going to take a brief look at what this involves. Given Python's source code along with Python's standard library, it's easy to derive the abstract syntax tree of the program. Once the abstract syntax tree is obtained, we then map parts of this tree to the symbolic control flow graph obtained by analyzing the source code. Using this relationship, along with the output of the instrumentation algorithm over the symbolic control flow graph, we can determine which parts of the abstract syntax tree of the program we need to modify in order to insert instrumentation code. Once we've performed this modification of the abstract syntax tree, we compile it to Python bytecode and write that to a file.
Okay, are there any questions at this point? Maybe I can ask, so are users of your framework, do they use this visualization tool?
We built simply just for things like this. We built that just for things like this. So
okay, for tutorials
yeah,
only, right? They trust that the instrumentation work as it is supposed to work.
Yeah, so far we if there are, so it's a difficult thing to debug when the instrumentation goes wrong.
Of course. Yeah.
So it helps. It could help us, but yeah, so far we've had to trust in the instrumentation working. Of course, sometimes there are cases where we haven't seen because the instrumentation requires a lot of static analysis of Python, and that's something that people don't tend to do much. So there aren't really any pre-built libraries for it. So all of that had to be built from scratch. So there are still we still find things where we haven't thought of a case in how the abstract syntax tree can look. But yeah, in general, we're sort of building up our level of trust in the instrumentation as we know that we're covering more and more cases.
Thanks. Any other questions? If not, maybe we can continue with the third video, which is a short one, I think.
Yes, it's the short one. Just a moment.
We will now consider the problem of determining whether or not a program satisfies a given CFTL specification based on the data given to us by instrumentation code that we have placed in the program. When performing online monitoring in general in runtime verification, at any given point in execution we haven't yet observed the complete program run. In our case, this means that the online monitoring problem reduces the question of does the prefix of a dynamic run observed so far satisfy a given CFTL formula. What we do to answer this question is generally referred to as incremental monitoring. We use this phrase because at runtime we have to deal with incremental updates to the prefix of the execution that we have observed. These incremental updates to the execution must then translate into incremental updates in our decision on whether or not the program execution has satisfied the CFTL formula so far. Our monitoring algorithm for control flow temporal logic uses a form of formula rewriting. Whilst conventional formula rewriting techniques suffer from the fact that rewriting formulas can lead to vast increases in formula size, CFTL admits a rewriting scheme that allows a monotonically decreasing size of the formula. Formula rewriting for CFTL formulas is achieved using simple and/or formula trees. These formula trees are collapsed as data is observed at runtime from instruments placed in code. In runtime verification, monitoring has historically been made more difficult when formulas have quantifiers. To ease the situation when monitoring control flow temporal logic, formula trees are grouped by static bindings that are identified during instrumentation. Each instrument placed in the code contains the static binding for which it was placed. Finally, special trigger instruments placed in code around static bindings cause instantiation of new formulas, and this is how we handle quantification. At runtime, once the set of formula trees is obtained using the static binding found in an instrument received, we then use the atom also stored in the same instrument. This tells us for each relevant formula tree that we found, which part of the formula tree, and in particular which leaf, that we should replace with the measured value. For example, in the case of the formula tree on the left, we would have two measurements. First, the value of the variable a in the state q, and then the duration of the next call of the function f along from the change of a. As these two measurements are made at runtime and received by the monitoring algorithm, this formula tree would be progressively collapsed until the final truth value would be obtained. We'll now take a look at how monitoring works in practice with the VyPR tool. So this is the part of our visualization tool that's dedicated to the monitoring side of things. So the idea is that instrumentation happens statically, performs the necessary modifications on the source code, and compiles the bytecode, and then when the program runs with instrumentation, the monitoring thread run by VyPR receives information from the instrumentation code, and this visualization tool shows us what happens. So we're trying to monitor for this specification, as we saw previously in the instrumentation visualization before, and we want to check this code. Again, it's the same as what we saw before. So our first event is that the function starts because we write CFTL specifications over individual functions. And the next event is that a new monitor should be triggered, and this is a new formula tree. So if I go to this event, we'll see that again, these monitors are organized with respect to static bindings. So as we saw before in instrumentation, there's a static binding picked up on line 9. So on line 9 equals 10. So I add a monitor to this set of monitors, and my monitor is essentially a formula tree. So here I have time between, and I have two parts of it, and ultimately I want to observe measurements for these two parts and decide whether my formula tree collapses to a truth value or not. So if I go to the next event now, I see that first of all I receive an observation from the instrumentation code. In this case I receive a timestamp, and the formula tree hasn't collapsed yet for the simple reason that part of it hasn't been resolved yet, so it can't collapse to a truth value. So if I go to the next event, which is receiving another measurement, then you see now I have these two timestamps, and I can determine the amount of time elapsed between these 2 points in the program execution. So the next event is a collapse monitor event, and this means that when VyPR was running, the next thing that happened once it received these two measurements was that it decided that the formula tree here could collapse. And this is equivalent to the formula tree yielding the verdict. So in this case, we determined that the time between these two timestamps was indeed inside this interval that we've defined here, which is the closed interval from 0 to 0.5. Now, if I play, I see that this happens automatically, and I can keep collapsing like this. And if I scroll along the verdicts a bit, you can see that I get two verdicts because my specification in this case only has a single quantifier, so I only capture these two changes of A, and then I only care about the next call to calculate something along from each of those changes of A. Now, if I were to include a second quantifier, then the monitoring story would look very different. And for example, here we have the for loop. So for each of the iterations around the for loop, if I had a second quantifier that captured all of the calls to calculate something in the future of this change of A, then all of the calls of calculate something inside this for loop would be captured, and we would get a formula tree for each of those. That's it for the first half of this tutorial. In the second half, we'll present our explanation approach for property violations. We'll describe our tool ecosystem that allows software engineers to use runtime verification for performance analysis in the software development process. And finally, we'll describe an application of the VyPR tool system to analyzing a real system running at the CMS experiment at CERN.
Okay, short part. Are there any questions?
Yes. Do you have any, for these timing properties, do you have any idea of how much the instrumentation affects the timestamps? And
So in terms of the overhead,
yes, and
yeah.
of the precision of, did you run any experiments on the instrumented versus non-instrumented?
Yeah, so we've, in terms of the overhead, for the systems that we've run on, we ran experiments that lasted for about a day, that were based on some repository of data that we have that we can sort of process and monitor the behavior of the system while processing. And the upper bound of the overhead was around 5%, and normally it was below that. And well, the reason for that is just because instrumentation is quite conservative. We never say that. We make a point of not saying, of not comparing our overhead to profiling. So at the beginning of the talk, we say, well, you know, profilers, when we talk about profilers, we only highlight the fact that they generate a lot of data. We don't say that they generate a lot of overhead, because it wouldn't be fair for us to say that we beat that. We beat that because we know exactly where to look, whereas profilers are giving you everything. But yeah, in general, we've been below 5% with our experiments. It's possible to make that go a lot higher. So one of the ways that VyPR works at the moment is that because we use threading, if either of you know much about the sort of internals of how the Python interpreter works, you'll know that the multi-threading system used in Python is a little bit controversial, meaning that the safety mechanism used is basically results in certain types of programs, despite the fact that they're threaded, being effectively serial. So there are ways such as, if you monitor a program with VyPR that doesn't have a lot of I/O, that has just a lot of memory operation, doesn't write to disk a lot, then you'll blow the overhead up because the program will essentially run serial. You can fix that by using multiprocessing instead, but yeah, there are cases in which we can make the overhead go up. We know what those cases are, and there's a way to fix those. But in our cases, where we have web services, so the I/O activity is very heavy, as you can imagine. So in those cases, the I/O the overhead, sorry, is very low.
Maybe I can also ask, do you have, about the specification language, do you have some special constructs to deal with loops and periodic behavior? I would imagine measuring something like, okay, what is the duration of a loop until I reach the very same control point is an interesting.
So for that, that's one of the reasons why we introduced the multiple quantifier feature. So before that, we just had one quantifier, and then we were seeing that, well, there are a lot of things, you know, for example, with loops, as soon as you have a loop, that becomes really difficult to deal with. We also will introduce in the second part how we deal with being able to, well, we'll introduce a formalism that could be used to analyze loop behavior. So we don't talk about it explicitly here, but we can deal with loops, let's say in the offline analysis, in the explanation part of the work, where we can look at how many iterations were completed and things like that, and sort of combine that with the verdict data that we get out of monitoring.
Good. Thanks. Yes, I think then we can continue with the second part.
You're not waiting for me to do something, are you, just to make sure? Oh, good.
No,
We'll begin this second half by describing our approach for explanation of property violations in control flow temporal logic. Our ultimate goal in explanation is to point out to software engineers the differences in characteristics between dynamic runs that violated a specification and those that satisfied it. Our work specifically focuses on extracting information about how program paths vary. This is possible because of the low-level nature of control flow temporal logic. For example, in the case of the formula on the left, we have the time between operator, and this places a constraint of the time taken to reach the call of the function calculate something from the change of the variable a. Specifically, if the control flow between these 2 points in the source code were to have different possible paths, then we would be interested in whether certain paths would be responsible for a higher time between the 2 points. Now, before discussing our theoretical contributions in depth, we highlight that theory is only part of a successful explanation approach. The results of any approach must be made available to software engineers in an actionable format. So in this section we present both our theoretical contributions and the layer that makes them useful to software engineers. As I mentioned previously, because of the low-level nature of control flow temporal logic, we will focus on explanation by analysis of program paths. In particular, we will introduce an approach for comparing paths taken by multiple runs of the same function, since control flow temporal logic formulas are written over individual functions in a system. We don't yet consider explanation using interprocedural paths, but we highlight that analyses like this are possible using the offline analysis tools provided by the VyPR ecosystem. Now, the ultimate aim of using program path analysis for explanation is to derive a set of points in a function's code at which a set of paths disagree, and then combine the subpaths taken at those points with information on specification, satisfaction, or violation. To illustrate our work here, we will be using our case study at CERN as an example. Here we see a code listing that is representative of our case study at CERN. In particular, we have a condition with another conditional nested inside the first clause, and then we have a try except block afterwards. We will be interested in measuring the time taken to move between the initial assignment of P at the beginning of the code and the final call of the database commit function inside the try except block. Now, we know that paths will differ at the first branching statement, but recording the predicate P may not be space efficient. Further, the control flow in either clause may also be non-trivial, so recording only P may not suffice. Ultimately, we can conclude that we need a more general approach for recording and comparing program paths. Our approach to recording and reconstructing program paths consists of a 3-stage process. First of all, we insert instrumentation code at branching statements in code, identified using the symbolic control flow graph. Second, we use the instrumentation code to build up a program path, and the third step is done offline. In particular, we reconstruct program paths as paths through symbolic control flow graphs, using sequences of conditions built up by instrumentation. Here we see the same code listing as before, from our case study at CERN, along with 2 instances of its symbolic control flow graph, each one showing a possible path through it. This sets up our consideration of the path comparison problem. In particular, in this case, we see that we have 2 paths, each diverging at the same point, namely the first conditional in the code. We would like to be able to detect this divergence automatically given an arbitrary set of paths. Our approach is to use context-free grammars. Now, the first question to ask here is, how do we transform a symbolic control flow graph into a context-free grammar such that any path through the symbolic control flow graph can be represented with respect to that context-free grammar? Now, a possible solution here would be to see that a symbolic control flow graph could be converted into an automaton, and then from here we can use an established algorithm to convert the automaton into a context-free grammar. However, this makes seeing divergence and later convergence quite difficult, so we propose an alternative approach. In particular, we remove the automaton stage altogether, and instead we convert symbolic control flow graphs directly into context-free grammars, but which acknowledge the special structure of symbolic control flow graphs. Our technique allows detection of disagreement and, significantly, later agreement. The translation from a symbolic control flow graph into a context-free grammar involves mapping non-terminal symbols to symbolic states and terminal symbols to edges. This carries the intuition that a path through a symbolic control flow graph is a sequence of edges. Therefore, any context-free grammar should generate a sequence of edges. And here we have an example segment of a context-free grammar. In particular, we have the vertex, which signals a call of the function self.processIOVs, and from this we can generate an outgoing edge, and then the next vertex along, which signals both a change of the variable new tag and a call of the function func. Now, as usual, this rule would be recursed upon, so the vertex with the new tag and func would be used to generate another outgoing edge, and this would carry on to generate the entire path. And now we see the first example of our scheme's acknowledgement of the special structure of symbolic control flow graphs. In this case, we show the rules that are used to generate paths through conditionals that are identified. The first step in this recognition is by identifying that a vertex, in this case P and predicate 1 at the top of the symbolic control flow graph, leads into a vertex that is the beginning of a conditional block. We can see that the difference here is that because we've detected that this vertex leads into a conditional block, the rule is written differently in the context-free grammar. First of all, we get the normal outgoing edge, and then the subsequent vertex, in this case conditional, But then we also include the post-conditional vertex. We do this because the resulting structure of parse trees with respect to this context-free grammar allows us to do certain operations that ultimately detect divergence in paths. By applying our full scheme from the inside of a symbolic control flow graph towards the outside, we get a context-free grammar like the one shown here. We see that non-terminal symbols on the left, highlighted in red, are vertices, or symbolic state from the symbolic control flow graph, and on the right we have terminal symbols as edges, and then further non-terminal symbols that can be recursed upon to ultimately generate paths. In the first example highlighted here, we see a normal vertex with no special structure, so the right-hand side of that rule in the context-free grammar is just an edge and then a subsequent vertex. We also see that the vertex at the beginning of the conditional block allows one to generate paths through either clause of the conditional. Now, important to notice is that the vertices at the end of a conditional block also have special structure. In this case, we see that one of the vertices at the end of the block only maps to an edge and not to the subsequent vertex. This is because the subsequent vertex is a post-conditional vertex, and this is included in one of the rules that we saw earlier. Again, this special structure of the context-free grammar allows us to generate parse trees that make the detection of divergence in paths straightforward. We'll now see two examples of parse trees derived for paths with respect to the context-free grammar derived from this symbolic control flow graph. So here is the first, and here is the second. And it's already clear that these two paths generate quite different parse trees. Now, our approach for detecting disagreement in paths revolves around intersection of parse trees, which yields leaf nodes with vertices. Since vertices are symbolic states, which are non-terminal symbols, we know that parse trees like this are representative of the disagreement between multiple paths. In particular, to represent this fact, we refer to these significant vertices as path parameters. This naming convention carries the intuition that vertices can be given values, in particular subpaths, for a region in which multiple paths disagree in code. Now, to reiterate on our previous point, theory is only as useful as its interface with its users. If a tool is badly designed or requires too much familiarity with the underlying theory, the utility of the underlying theory does not really matter. This is the problem that we address next. To provide an interface between our underlying theory and the software engineers who will use it, we've developed an ecosystem of tools for instrumentation, monitoring, and explanation. For example, we have the VyPR core, which is highlighted in red, and this consists of the specification library, the instrumentation process, and the online monitoring. We also have the server, which consists of an insertion API, an analysis API, and a relational database to store all of the data obtained during monitoring. And finally, in blue, we have the analysis tools. And these consist of a web tool, which we'll demonstrate later, and a Python library, which we'll also demonstrate later. We provide a web-based analysis environment as an analysis entry point. The idea with this tool is that very little knowledge is required of the underlying theory. Instead, software engineers can explore the data obtained during monitoring using an intuitive and powerful web interface. For cases where more complex analyses are needed that can't yet be performed with the web tool, we provide a Python library. And while this requires more knowledge of the underlying theory, it allows significantly more flexibility. Our web-based analysis environment is a web application that wraps around a dataset generated by VyPR's instrumentation and monitoring processes in order to provide engineers with a visual interface for exploration of verdicts. The general pattern of use is exploration of verdicts in order to observe incorrect behavior and then ultimately to explain it. The architecture of the web tool is as follows. We start with a dataset obtained by instrumentation and monitoring, and then the web interface's backend performs some post-processing to get certain explanation data ready for the engineer to use. The web interface then allows verdict listing, measurement plotting, and path comparison and highlighting. Ultimately, all of these features are exposed to the software engineer through an intuitive interface, so quite complex and sophisticated analyses can be performed using just a few clicks in the web browser. We'll now give a live demonstration of the web tool being used to analyze the performance of a service used at the CMS experiment at CERN. So this is the first screen that you see when you open the VyPR analysis environment. So we see that on the left we have the list of specifications written across our service. So this is the service that we've applied VyPR to in our CERN case study. And on the right here you see an area where we will soon see a specification being listed as well as a code listing. So for this initial example, I'm going to select this specification that's written over the check hashes function. And this is a specification that places a constraint over the amount of time taken by a function called find new hashes. So I'll select that. And the next thing that happens is I get a list of function calls. So I can scroll through and select these individually. However, given that in this case there are 4,000 function calls, we have the option to select all the function calls within an interval. So another thing about this display is that, first of all, you get the timestamp of when the function call started, you have the duration in seconds, and then you have the result of all of the specifications over that function with respect to the one that we selected. So we go back here, we wait for it to load again, because 4,000 calls, and so we see here the first one. This means that there was a verdict during this particular function call that was false. This green indicator means that there were no verdicts that generated false, all of them generated true. So now I'm going to select all of the function calls between 1254 and 1330. So now I click filter calls, and you see that all of the function calls, all of the relevant function calls have automatically been selected. Now the key next thing to see is that the specification has been left alone, but in the code listing, we have this highlighting of relevant lines. So the first line that's been highlighted is the line hashes equals, and then all of this stuff on line 251. And this is the line that's relevant to the quantifier in our specification. So to reflect this, we show that, first of all, it's a binding, so binding an index 0. And we make this clickable. So when I click here, the next thing for me to do is to select part of the specification, which under the binding that I've selected, I want to see measurements from. So if I now select this q.next call of find new hashes, then this will start from this line and show me where instrumentation identified other points that satisfy this predicate of something being a call of find new hashes. So I click here, and you see that now I get some options over this line, which is a call of find new hashes. So I click here, and well, I get 3 options now. The first one is that I can plot the severity of observations from this point, and this essentially means that we will take all of the measurements with respect to this specification, and we will plot some metric of how close those measurements were to satisfying this specification. So if they succeeded, then we will display them in a certain way, and if not, then we'll display them in another way. So I'm just going to open this plot now, and if I drag this into view, you see that a notion of severity is reflected by this negativeness of the values. So we know that if we drag the window down, we're measuring a time duration. So obviously this won't be negative. These measurements will not be negative. And so here we see that we have negative values because the notion of severity reflects whether or not something went well or badly. So in this case, we have some violations. So if I filter out all the successes and I just want violations, then I see that, well, there's one here that has a severity of -10. And this just means that it was outside the interval defined by the specification by 10 seconds. And it's here. If I have -207, then this was quite a bad violation. It means that the measurement was outside the interval by 207 seconds. So you can see that's quite a major failure. So now if I turn successes back on, you can see that these are all relatively small, and this is a characteristic that we often see in severity, which is that the violations, the bad violations, are often much worse than the good successes. And this is because, well, this is a natural characteristic of the fact that the only region inside which measurements can be good here is quite small, and the region in which measurements can be bad is, well, mathematically infinite, but practically it's much, much larger than the interval in which good things can happen. So of course, all the things that are bad will be in a much larger interval, and they will be drowned out a little bit. So if I now just list the successes, you see that the best severity that we observe is 0.11. So much smaller, much lower order of magnitude than the violations. So now I'll close this plot, and now we'll look at the observations. So the observations are all positive, and these are just measurements. These are in seconds. So here I have the 207 second one, but we'll see that, for example, if I go back to the severity, then we'll see that the highest severity will just be 0.3 away from the highest observation. So if I again open severity, then we see a difference of 0.3. And this is, not surprisingly, the upper bound of the interval in which good measurements are classified. So if I now open the plot of observations again, we see that there are many very small times taken and only a few quite large amounts of time taken. But in this plot, there's no information about how things went with respect to the specification. These are just measurements that were taken in order to decide whether or not the specification was in fact true. Now, another thing that the analysis environment allows is that we can, for example, plot, or we can highlight the paths taken or up to a given measurement. So in this case, I have this line here, and it's quite clear that the program had to take some path through its code to reach this point. So in this case, there's only one path, and so we're about to see pretty much an error because no path comparison can happen. So if I click highlight paths by average verdict severity, then first I get this notice at the top that all the runs took the same time, analysis by path is unavailable. But you can see that now we highlight all of the instructions that were executed on the way to this instruction. And while in this case that's not very useful, we'll see in another specification example that this is an incredibly useful thing to be able to do. So now we'll look at another specification which is a more complex one with multiple quantifiers and multiple types and a different type of atom, sorry. So here you see we have, first of all, we have a one for all, and then we have a second for all, and this is essentially just tracking all the things that happened in the future of this quantifier up here. And then inside the specification, we have this mixed atom. So first of all, we care about the time taken to get from this state Q to this state, which is at the end of the next call to this other function. And then once that happens, we care about whether it's in this interval 0 to 0.1. And I can already tell you that this constraint is very tight, so we'll see a lot of violations. And as you see, we see a lot of red going down here. So this was an early version of the dataset before we realized that this constraint was too tight and that we had to loosen the constraint in order to actually see how the system was really behaving. And this is an important part of writing specifications, actually tuning them, because at the beginning you might write a constraint that's way too loose, and so you don't find any actual information about your system. And you might also write a constraint that's way too tight, in which case apparently your system is always behaving badly, but in fact the specification doesn't describe well the expected performance of your system. So again, we're going to show this time, and I'll filter this. So an important thing when we do this, when we select function calls, is that the bindings that are displayed in a code listing on the right are reflective of what is executed across all of these function calls. So if I were to deselect all of these and then just select one, which only traverse one path, then a couple of these bindings or one of these bindings might disappear. So in this case, we've selected quite a few function calls, so across all those different function calls, all of the paths have been traversed through this function, so we list all the bindings. So the most interesting case here is if I select binding 1. And this is, so you see we have color coding, we have turquoise matching this statement because, well, this was a change of the variable self.destination tag name. And here we have a call of session.commit, which is in the future of this change here. So, well, first of all, this is where we have two bindings, because if we click here, then we have two future calls of session.commit. So this will generate two bindings during instrumentation. And then second of all, once we click on one of these bindings, we see that now we have a slightly different selection process that we have to go through in order to narrow down the points in the code that we care about. So first of all, the selection here is slightly different to the previous example. And this is because in the previous example, we had this binding, we had this quantifier, but then the specification was doing some kind of transformation on what the quantifier was giving it. For example, we had a change of a variable, and then we had the next function call along from that variable. In this case, we don't really do any of that. We just take Q, we take it as it is, we don't do any further traversal on the code, and we take C.result. So we're not doing any complex traversal on the code, we're pretty much taking what we get from the quantifiers. So at this stage I have two options. I can either select or fix one of these lines that is associated with the variable q, or the one that's associated with c.result. So I'm going to go with q, and I'll see that when I do this, I get an options button next to the appropriate line that is belonging to the variable q, because q is all changes of this variable. So if I click this, the one option that I get is that I can select this statement and highlight others that could form a pair. So an important thing to realize here is because we have a mixed atom, in order to do any kind of plotting of any data from it, we need 2 points to fix or to select to know which measurements came from those 2 points. If we only select one and we want to narrow down the measurements by which places in code they came from, then we have a problem, because we then have to select data from multiple points in code, and plotting it becomes a little bit nonsensical. So we have to select the 2 points that correspond to the two parts of this specification. So I'll now click this, and this will tell me that, okay, the next thing you need to look at is down here. So this means ultimately that I've selected binding 1. Binding 1 was these 2 points, line 42 and line 117. I then clicked Q, which mapped to this line, and then when I went to select the other line that formed the pair so that I could measure the time between them, the only other available option was this one, because we've already fixed the binding. So now here I'll click Option, and we have a few different things that we can click. So first of all, I can select the statement and just plot observations, so I'm going to do that. And you see that, well, all of them, if we look at our specification, the upper bound is 0.1, and well, all of them are above 0.1. So these are observations of the time taken to reach this statement here from this statement here. So you can see that this is a really useful interface in that we can actively interact with the code and plot measurements taken from the parts of the code that we've selected. So that's quite a powerful ability to have when you're analyzing your code. So I'm going to close that and now open a separate plot severity window. And you can see here, as expected, all of the severities are negative because every observation is a violation. If I just display successes, then I won't get anything. And also, as you can see, there's some quite severe violations down here, but most of them are actually quite close to the interval that we wanted. So it's also a useful thing to be able to do, to look at one of these plots and use it to be able to tighten your specification and say, well, it looks like more of the observations that we're getting in this case are possibly around 0.5. So if I maybe tighten my specification up here to 0.5, then the violations of my specification will reveal more insight, because they'll be the ones that actually do take a long time, rather than the rest of the observations here, which are quite clearly just the normal behavior of the program. So now that we've looked at these two, we can do the really interesting part of this analysis of this specification, which is we can take advantage of our path comparison machinery, which is implemented beneath all of this interface, and you can use this to detect the different paths taken and ultimately plot the times taken by the program when it traverses either of the paths. So I'm going to start this off by highlighting the path. So you see now that the code expands so that I can see all of the code, and the different paths that were taken are now highlighted. So first of all, I have highlighted in blue the instructions that were taken by every statement. So here you see I arrived here, and then I started from line 42 and I took these other statements here. But then I arrived at this conditional, and our path comparison approach has automatically detected that at this conditional there's divergence. And what we normally do is use the color to highlight the average severity of verdicts across each of these paths. But in this case, we have a lot of similarity. So what we'll do is click on this conditional, and we'll be given the option that we can either plot the observations with respect to the path taken or the verdict severity. So since all of the results in this case were violations because our specification was too tight, I'm going to just plot the observations, and you see that now we get this nice window where on the left we have a plot of the time taken, the measurement taken, and on the right we have the same code listing again. So we have the same code, as you can see, but we have this detected path difference where we can select which path that we want to analyze. So here we have the path starting on line 49, which is the first path through the conditional, but then we also have the path starting on line 88. which is the path down here in the second clause of the conditional. So if I select the other one, then my plot changes and I see different data. So I can really see how my code performed with respect to the path that was being taken. So this is a perfect way to be able to see whether the performance of your code depends on the path. And this is, as I've said in the previous slides, a step towards being able to really explain what your program is doing with respect to the observations that you measure.
Okay, are there any questions to the explanations part?
I was muted. I would like to ask you, so you implemented quite a sophisticated visualization of this monitoring, and from the users who are using your monitoring tool, what is their feedback? What are the features that they like, the features that they find less interesting? What do they think that your framework is missing?
So far, because we're in the prototype stage, we are just beginning our plans to let people use this web tool. So it's pretty much just reached the end of its development lifecycle, let's say. And we have a couple of places where it's going to be used. So one of them where it will be used immediately will be, so we've done some work on continuous integration, and it's a nice opportunity to explore the results of CI along with performance, so that will lend itself well to that case. It's being used, as you can see, to replicate some of the analyses that have been done on one of our critical services. So that was done by our team. So by me and by a couple of other people. And then the other use case that we're planning will start quite soon, and will be from a completely separate team. So then we'll start to, that will be the proper evaluation, and I guess the proper trial of how well we've really done. But we tried to expose as much of the, let's say, the power of the underlying formalism in a nice interface as possible. But there are some limitations. In the next part, you'll see how we handled that. But yeah, we're sort of at the end of transitioning the theory into a usable thing, into a usable tool, and now we're beginning to be able to give it to people and actually deploy it.
You're muted.
Yeah, you're muted. Sorry.
Yeah, sorry. From your perspective, what would be some useful features that are still missing and that you would like to have?
So one of the things that can be done, one of the nice things that we've used for analysis has been that if you apply VyPR to programs on two separate machines, for example, the service that was being analyzed in the video you just saw, that consists of a client and a server machine that communicate with each other, and there are multiple clients. And so we applied VyPR on both sides, and then we combined the performance information, and we looked at how the performance on the server side was affecting what was being observed on the client side. And that would lend itself very nicely to visualization, because at the moment we sort of have this, let's say, naive visualization where we just, as you see, we list the functions and then we list the specifications for each of those functions. We have some acknowledgement in the interface at the moment of the fact that we detect that multiple machines have been involved in the monitoring, but I think there's room for making that a bit nicer to analyze. And the other thing is that because we collect information about the functions that generated certain performance data, part of that information is the times of those calls, so we can build a call tree. So it would be nice to see that call tree and to be able to explore whether the performance in one part of your system affected performance further up the call tree and things like that. So, yep.
Thanks.
Okay, maybe I can also ask, so the quantifier free part, do you look into this part in more detail when you are trying to explain something like that? Because I understand that this can be an arbitrary Boolean combination of yeah, measurement comparisons or something like that, right?
Yeah, so formally we have a notion of the part of the specification that fails. And this is not necessarily unique because you can write specifications such that multiple atoms place different constraints over the same thing, over the same state at runtime. So we have a notion of the set of points in a specification that cause failure. So based on that, then we can say, okay, well, we can look at what those atoms look like and then apply a different explanation procedure. So for example, if one of your atoms just measures the duration of a function, then what you would care about is if you are also monitoring the code inside that function, then you might care about the path taken inside that function, so you can link up the data in that case. But then if you have a specification that asks for the time between 2 points, then as you saw, you care about the path taken between those 2 points directly in the code. So we essentially take the atoms from the specification, look at the structure, and then we have a discrete set of possible explanation approaches we can use, and then we use the one that's appropriate to the atom.
Thanks. Okay, if there are no further questions, we can continue with the fifth and last part.
Now, for the cases that the web tool doesn't cover, we've introduced a Python-based analysis library. And this is inspired by the Object Relational Mapping, or ORM pattern. This allows scripted analyses with comprehensive access to the data collected at runtime, whilst hiding complex post-processing steps. The general architecture involved with analysis scripts is that we start with a dataset from instrumentation and monitoring, just like with the web tool. We use an analysis API provided by the web tool, and then via HTTP and post-processing it into objects, we arrive at a point where we can do analysis using the library. In particular, this includes querying across the entire schema, performing path comparison and highlighting, and further call tree construction, which is not yet possible with the web tool. All of these features can be combined to do some sophisticated offline analyses, which include collecting data from multiple machines in order to detect whether the performance of one machine affects the performance of another that communicates with it. We'll now demonstrate how our Python library can be used in the Jupyter Notebook setting. So this is our first example of the VyPR analysis library being used to analyze performance data taken from a real-world system. In this case, it's our case study from the CMS experiment at CERN. And in this case, the service that we're analyzing is a service that takes data from runs of the Large Hadron Collider at CERN and uploads that data into a central database ready for certain activities to be undertaken by physicists. Now, the architecture of this system is distributed between a client-side and a server-side process. The client-side proposes data to be inserted into a final database, and the server-side receives the data and decides whether or not the data can correctly be inserted, whether any transformations can possibly be applied to the data so that it might be more appropriate for inclusion in the final database, and ultimately has to do all of these things within reasonable time. So we care about analyzing its performance in different ways. Okay, so the example that we show here includes trying to determine whether an optimization that we know will add a bit of extra time onto the process is actually effective enough to justify the extra time that we spend on it. In particular, when we send a lot of the data over the connection between the client side and the server side, we segment it into parts so that we can deal with an unstable network if we have to. But one of the problems is that quite often a lot of these segments of the data don't need to be uploaded, and if we were to upload them, we would take a lot of time and ultimately be wasting that time. So in this case, we care about trying to decide whether the optimization that we've employed to decide which bits of data should be sent is happening quick enough so that we can justify that extra time that's being spent on it. Because ultimately, if the optimization takes too long and it isn't really being that effective, then we may as well just turn it off. And in addition, we're interested in the cases in which we could turn it off versus the cases where we definitely know that we have to use it. So we start as normal with the analysis library by importing whatever things we need from the Python standard library as well as some other packages. But most importantly, we import the VyPR analysis library as you see here. We then take two steps. The first one is to prepare a dataset that we have, a local dataset, and this will have the effect of taking this database and starting up the central analysis server based on this dataset. We then set the directory of the local monitored service because we have the code locally, and this is needed in places where, for example, we want to do path comparison. So if you now run this part of the notebook, we see that we're setting up the server in the background using this database, and finally we've connected to the server, and now we output, just to be sure, the directory inside which the local monitored service is kept. Now our next step is to use a few of the functions provided by the analysis library in order to carry out our analysis. So the first thing that we do here on the first line is to get the list of functions, and we care about the first function. And the first function in this case is the function that carries out this hash checking optimization that you see here. Once we've got that function, we then get all of its calls that have been recorded by VyPR, and then from there we can begin to iterate through that list of calls and then perform our analysis in each case. So our analysis in this case consists of first getting the single verdict that was obtained, because in this case that we know from domain knowledge that there will only be one verdict because of the structure of the code. And then either we care about all of the failures or we care about them all. So in this case, for this analysis, we care about getting all of the data regardless of the verdict that it generated. So we say, okay, for each call of this function that took care of what we call the hash checking optimization, then first of all, we get the verdict that was generated by that call, and then for each verdict, we get the observations. And the observations are just the measurements that were needed to check whether that verdict was true or false or not. For example, in the web tool that we saw earlier, in the specifications listed, in a mixed atom, we might need 2 observations. So in this case, you see that we get a list of observations, and then we take the left-hand side observation and the right-hand side observation. And in both cases, we use a filter, and we care about, okay, the left-hand side observations should have the subatom index 0, and the right-hand side should have the subatom index 1. And in each case, we just take the first thing that we find. So now we care about processing this data that was observed and extracting the important part of it, and this is what this part is for. I won't explain fully why that's needed because it doesn't really add to our explanation of the analysis library, but we can see here that we begin to build up a dictionary that maps hash lengths to how many were not found. The idea here is that for each number of hashes that we have, we maintain a list of all the hashes that were ever not found when that optimization was run for that number of hashes. So here, if I run this, then I'm going to fast forward through the analysis now, because this takes some time. Now, in particular, this is communicating with the server for every iteration, so this is actually quite a slow process. Now, future work and future plans involve trying to speed this up by reducing round trips to the server by, for example, just sending one request or just a couple of requests with all the information from all of the queries that happen inside this for loop so that we can get all the data back in one go. So now that the analysis is finished, we can carry on to the next step of the notebook. And from here, I won't explain in depth what the code is doing because it's generally using other libraries and doesn't really show much of the analysis library being used. But this step is essentially going from the for loop that we saw earlier, from the map from numbers of hashes to numbers of hashes not found, and it converts these to percentages so that we can bin these percentages and put them into a plot. So if I run these steps, I run this, and then finally I run my plotting code, and this will ultimately, as you see here, yield a box plot. And you can see that, well, most of the times the percentage of hashes not found is actually quite high, so the optimization is doing a good job. But in this case, we can't see it here, but I can say that the hashes are always new. So out of the 4,000 function calls that we have, we see that of the ones that sent a lot of hashes between 300 and 2,000, which is easily the upper bound of the number of these hashes that we'd have to send, we see that a lot of them, or all of them in this case, actually result in all of the hashes not being found. So the final stage of the analysis is that we tear down the server, and if we run this, then the server will be stopped, and everything will be ready to do another analysis and run another notebook. Our second example of using the VyPR analysis library involves analyzing the behavior of some code with respect to a path taken. In fact, we'll analyze the same case as we showed in the web tool earlier when we analyzed the difference in performance between the two paths. But in this case, we'll do the exact same analysis, but using the analysis library. Now, the same as before, we start by importing the setting a given data set, and then setting the local path where the code is found that we're going to be analyzing. And then we do include an extra input here, which is the machinery that is needed for path comparison and how it's implemented in VyPR. So we'll run this, and this will set up the database and start up a server in the background that wraps around this database and gives us the endpoints that we need to do the analysis using the analysis library. So most of the major logic in this is performed quite early on. So in this block you see that first of all we get the metadata function that we care about, then we get the property over that function that we care about, and we'll use this later to make sure that we get all the calls that are, all the verdicts rather, that are relevant to that property over that call. So in order to do path comparison, we also need to construct the symbolic control flow graph in memory of the relevant function. Now this requires that we've told the VyPR analysis library where to find the source code of the service that we're analyzing, because ultimately this source code will be read in and used to generate the symbolic control flow graph. So we generate the symbolic control flow graph here, and the next thing to do is derive a grammar. And as we saw before, we need a context-free grammar in order to do path comparison, so this step is part of that process. And the next thing that we do, along with, in agreement with what we did before, is to get the list of calls. And here you see that we look at the metadata function, the relevant function in the service that we care about, and get all the calls of that function when we run it. And we then iterate through it, which is the same pattern that we used before. The one difference now is that when we get the verdicts for each of the call, now we care only about the verdicts that are relevant to a specific property. For example, if there are multiple properties being monitored over the same function, then the verdicts generated are different for each specification. So for each specification, I will get a new set of verdicts with respect to the observations generated for that particular specification. So I need to be precise when I get this data using the VyPR analysis library. But luckily, it's possible to filter this and to indicate which data that you want precisely. So once I've got these verdicts, because there might be multiple, I iterate through them, and then I say, well, I only care about the verdicts with the binding equal to 3, and such that the verdicts were a violation. Then, once I've gotten this verdict, I get the observations that were required to reach that verdict. From here, the next thing that I want to do is, as we saw in the web tool, I want to measure the time taken along the different paths taken to get between point A and point B, where point A was a change to a variable and point B was a function call. So to do this, the VyPR analysis library provides some nice functions that make this very easy. So first of all, I want to get the path up to the observation that happened first, and to do this, I get the first observation and then call reconstruct reaching path along with the symbolic control flow graph that I constructed earlier. I then do the same for the right-hand side observation. So the left-hand side observation was the change of the variable that we saw, and then the right-hand side observation was the call to the function right at the end of the main function body. I then want to calculate the path difference, and so here I do this in quite a low-level way. I just treat the path as a list in Python, and I use Python's nice slicing syntax to be able to essentially subtract the path reaching the left-hand side observation from the path reaching the right-hand side observation, because ultimately the left-hand side path will be a subpath of the right-hand side path, because the right-hand side observation happened after the left-hand side observation in the same function call. The next thing that I do is set up a parse tree. And so earlier how we discussed that we need to construct the parse trees of the paths that we care about so that we can intersect them, this is what we do here. So we instantiate a new parse tree based on the path difference that we have. We're using the grammar, and then starting at the initial state of the first part of the path difference. Now this is a technicality and requires a little bit of knowledge of the underlying theory, and this is one of the reasons why the VyPR analysis library is more useful and more flexible, but requires a lot of knowledge of how things work underneath. So the next thing that we do once we've got the path is to get the timestamps measured on the left-hand side and the right-hand side, and then calculate the time taken. And we then add these pairs so that we have a correspondence between the parse tree and the time taken. And finally, we calculate the intersection, and this, as we saw before, will tell us where the paths diverged. For example, if we take our parse trees and then intersect them, we will find out which nodes or which vertices in those parse trees relate to divergence or disagreement of the subtrees of the parse trees. So if I then run this code, so once we've performed the intersection, what we will have in memory is a structure representing the paths, the intersection of the paths, along with any point of disagreement, so that further on in our analysis, we can access those points of disagreement, and for each of the paths that were involved in the intersection, we can determine what that individual path did in that case. So if we now look at the code that we use to figure out which path took which possible subpath through the region of disagreement, then we see that the first thing we do is to get all the path parameters from the intersection, and this will populate a list for us. And then when we iterate through the list of parse trees, we use the path parameters that we've derived and then use a method called readLeaves, and this will give us the subpath that was taken by each of the individual paths in the intersection through the region of disagreement. And based on this, we can divide up our performance data with respect to the path taken. So if I run this cell now, then the resulting structure in memory is a map from parameter value indices. In this case, we just have two parameter values, so we have a map from 0 and 1 to the times taken for each of those paths taken. And now finally, we have the plotting code, so if I run this, this will generate a nice plot for us. And we can see that we now have two plots, each one corresponding to a different path taken through the code based on the analysis that we did in order to determine the possible ways in which paths could diverge. So as we see, we've roughly reproduced the plot that was given by the web tool, and in here obviously it required more work, but we saw that there's a lot more flexibility. So to conclude this tutorial, we have introduced the theoretical foundations and implementation of a framework for the performance analysis of Python programs. This has involved introducing 1. A new temporal logic for specification of source code level properties, 2. Instrumentation and monitoring approaches, and 3. An explanation approach. In a significant step towards making runtime verification a viable tool for software development processes, we've also introduced prototype tools for various kinds of analysis, including a web-based analysis environment and a Python library that enables software engineers to write sophisticated offline analysis scripts. But there is still plenty of room for improvement. In particular, we could develop more precise instrumentation approaches using data flow analysis. We could add features to the web-based analysis environment to remove dependence on the Python library. We could improve the expressiveness of control flow temporal logic while maintaining the trend of aiming for friendliness to engineers. And we will continue our work on integrating VyPR into software testing pipelines, which we've already begun in the context of continuous integration. Now that's it for this tutorial, and on behalf of the team, I would like to thank you very much for your time and encourage as many questions as you have.
Okay, let's thank Joshua for the nice tutorial. And let's see if there are some questions to this last part. I can ask maybe, what is it inherent that in the library you need to expose low-level details of VyPR as opposed to, well, in the graphical user interface, certainly you don't want to do that, but maybe you could hide the details also in the library as well.
Yeah, so we've tried to define methods and build the class structure that the library provides in as friendly as possible a way. And there have been small improvements even to the scripts that were presented here since we wrote those scripts, because the scripts that were presented here were not the latest, but not using the latest, greatest version of the library, let's say. So we could make that a bit easier these days. But yeah, so in terms of the scripts that we showed there, in how we use the library, I think we intentionally sort of used sort of the more low-level things, as you saw. Like, you know, when we were doing the path analysis, we were taking paths and manually manipulating the paths and manually cutting them up. I don't think a software engineer would ever want to do that, even if they were writing the code. So the fact that they're writing the code already means that they want to do something that the web tool can't do. But there are nicer ways to do the things that we just showed that require a bit less code or nicer looking code. However, there are still still things that we haven't really managed to make more friendly yet. For example, you see there's a lot of for loops involved, just because you have a lot of data that you want to iterate over, and it's the same. And I think in any sort of scientific computing or data analysis side of things, you have a lot of iteration, and your code can look a bit ugly sometimes. And so far, we haven't really found a way to improve that situation much, other than by wrapping everything in, as you saw, this object relational mapping. So the very first versions of all this stuff before the analysis library was written was querying all this stuff with SQL, because in the back end we have a relational database. We were querying all this stuff with SQL, then doing the post-processing manually and doing all these analyses. And it turns out that Python can't make everything look nice. So that certainly didn't look nice. And we've managed to improve it a bit, but yeah, there's still some things that look a bit messy, like the scripts that you just saw. They still look a bit messy, I think. Anyway, so
Thanks.
So I have a question regarding your explanation module, which is pretty nice. Did you think about going a step further, in the sense? So what the explanation module tells you, given a trace and a program and a specification, and you detect the violation, it gives you like what are the potential problems there. And I'm thinking in like several directions, like could you combine it with testing so that you generate other inputs to the program, and then some of them pass, some of them fail, and you use it to refine your explanation. And I'm thinking even maybe about the program repair. So it would be probably very difficult to do something formal there, like using games or whatever, because we are working with real programs. But maybe again, something that is data driven and that combined with testing, and that could give you some indication what could be changed to minimally changing the program to satisfy your property. Did you think about these directions?
So we have a plan as to how to combine the testing with and data with performance. We're probably going to start that soon, hopefully, and that will involve us being able to. So we already have some work on CI, and that allows you to put VyPR into CI and combine the testing results with the performance data. The next step along from there is to be able to record the data that was given to the tests that generated the performance data, and then, as you say, a natural next step from there would be to then categorize the data and to basically do a bit more in the direction of what the data looks like with respect to what the performance then looks like. So we hadn't actually thought of that. I think that's a really good idea. So thank you.
So it's a really interesting tutorial. Thank you.
Yeah.